And hello, welcome back. So we are going to define our front and back faces today. So in the last video we have already done the plate, which is the wall. We have defined the inlet, and we have defined the zero gradient planes. Let's do the front and back. So this is a z coordinate equals 0. It's a low z plane as before. And of course this is x equals to 0 or 1, and this is a large z plane, x equals 0 or 1. So now we want to have the x equals 1 or 2 versions of these two planes. So back in our Excel file, I'm going to just paint it over. And then quickly we'll just do the front and back. Okay, so these are the two planes we want to kind of deal with. So x equals 1 or 2. Okay, so x equals 1 is here, and z equals to 0, I think. Yeah, z equals to 0. I'm just going to highlight this. Then this is the other one. So this is a z equals to 0 plane. So that is the small z plane. Okay. And then we want the x equals to 1 or 2. So where will that be? This will be z equals 0 on this plane. Okay, so I'm just going to erase all of this. Okay, just erase all of this quickly. Now just redraw two new boxes. So now we are going to the front and back. Yeah, front and back. Okay, so we are looking at this plane. I like to use this lime green. This plane, we're looking at the front and back faces. So let's say we have this. So I'm looking at the front face. I'm looking at this back face as well. So the front face and the back face. So there's a z equals 0 and z equals 0.1. So we need this. We need these 4 vertices. 1, 2, 3, and 4, and then the other 8 at the back. 5, 6, 7, 8 will be at the back. There are 4 at the back. Excuse me. So we're looking at the z equals to 0 plane. So z equals to 0 is a small z plane. We look for the least x and y. That'll be 0.1. We add y. That'll be 0.2. We'll add x. That'll be 0.9. And it'll be 0.8. 1298 is the point. And we'll just copy this over. Okay. Right click to paste. This is the comments. Z equals to 0. Low z plane. X equals 0 or 1. Do a similar process for the other one. Hope you get the hang of it by now. If not, you can rewatch the video. So we want is z equals to 0.1. So this is a high z plane. Z equals to 0.1 and x equals to 1 or 2. So these are the planes we're talking about. So in the large z plane, okay, large z plane, we need the least x and y. That'll be 0.5. We add x, that will be 0.10. We add y, that'll be 0.11. Subtract x, 0.6. 5, 10, 11, 6 will be how we write our point. 2, 3, 4, there you go. Okay, z equals to, this z equals to 0, sorry. Z equals to 0.1, high z plane, x equals 1 or 2. This is x equals 1 or 2. So we just want to check x equals to 1 or 2. Alright, 1 and 2 are these points. And then 9 and 8 are these points. So that's x equals to 1 or 2. This is also x equals 1 or 2, except z is 0.1 this time, as you can see in this column here. So that is pretty much it for our geometry file. Hopefully things run well. We'll just quit the thing, and we'll need to change some of our boundary conditions that will be in the 0 folder. So we need to change our initial velocity. Okay, so our 0 gradient planes, where will it be? What are they called? Okay, we go to system and let's go to blockMeshDict. So we have, okay, I'm just going to paste this down. I think I want to copy all of this. Alright, I'll copy all of this and I'll paste it here. So it's easier when to see. You have to alternate tab and, you know, do all that kind of funny thing. Okay, so I want you to notice something here. 0 gradient plane, type is a patch. These are generic for boundary conditions. Inlet is also a patch type. Don't worry about what patch is. This is a generic boundary condition that is not a wall. Okay, wall, I mean this for IcoFoam you can yeah, you don't have to type wall here. You can actually type patch, because patch is a generic boundary condition for almost any kind of boundary. Okay, for IcoFoam case. But just for clarity, I mean, it's a good thing, good practice to put wall. In other solvers, you'll need to differentiate between the wall and the patch, especially, yeah, I think turbulent or something like that. I can't remember. But anyway, it's good to leave it as a wall. Okay, but the front and back, we must type it as empty. What does empty mean? Recall that we want to actually do a 2D case, right? So for 2D case, it's two-dimensional, that's one. But you look at the front and back. I mean, we look at this, we're actually defining a 3D kind of a block with a z width of 0.1. Okay, it's a z width of 0.1, but actually we don't want it to calculate in the 3D case. So if you don't want to calculate it in the 3D case, we must tell OpenFoam, okay, these front and back patches, these front and back faces, don't calculate anything. Don't try and do anything funny. If you don't type empty, then you'll need to specify some other boundary condition for it. For example, a 0 gradient boundary condition. But for now, we'll leave it empty because this is for a 2D case. Okay, I'll just type in here. Okay, insert. Okay, insert. This is for 2D case. Okay, so I'm gonna quit. Did I copy it over? Yeah, I copied it over mostly. So cd dot and I go to 0 vi view. Let's go to the 0 gradient. So what do we want to be our 0 gradient for? The velocity. Okay, we want that to be our 0 gradient planes. So I'm going to write 0 gradient planes here. It must be the exact same name. If not, OpenFoam will know what you're talking about. So 0 gradient planes. Then I'm going to write, which is safe. Then we want the no slip condition to be at, I think there's a plate somewhere. Well, I think I didn't copy it over properly, but I think it's plate. Okay, cd, yeah, system, vi blockMeshDict. Yeah, I forgot to copy this bit. This is important. Okay, quit. Let's go to 0. VIU. So this should be called a plate. Alright, that's what we typed here. Do it exactly the same. So the left side, which is our inlet, let's name it as inlet. Okay, and we'll call this inlet because we named it inlet. The right side we don't have to do anything because it's already the zero gradient plane. Okay, so I'm just going to comment it here so that we don't have to do anything. And then the front and back is also empty. We have to put the empty type both in blockMeshDict and in the velocity file. So this is actually initial velocity. Okay, the initial velocity file. So the internal initial velocity is 0. We can specify other values. Okay, and the inlet value is a fixed value, kind of velocity. And it's a uniform 110. That means 1 meter per second in the x direction, 0 in y, 0 in z. So the fixed value is as such. It's telling you that the boundary condition has a constant velocity boundary condition. Okay, so we're going to save this using WQ, and then we are going to VI the P. Okay, so again we have zero gradient here, zero gradient planes, and of course we don't need a bottom wall. Okay, let me QA, quit all. I forgot. Yeah, okay. So remember the plate type is actually no slip. Okay, we can use no slip, or we can use a fixed value of 0, 0, 0. You just want to be sure that we are putting in the right boundary conditions there. Okay, QA, that is quit all. No matter what happens, you can put an exclamation mark to force it to quit. So moving wall. So okay, you can see the changes are not saved. So unless you type the WQ option, it will not do anything for you. So the pressure at everywhere is just zero gradient. So zero gradient planes is zero gradient. The plate is also a zero gradient for pressure because we don't want to touch the pressure, so to speak. Planet, yeah, type planet. Oh my goodness, I type planet. Okay, it's not planet, it's plate. And yeah, so plate, not planet. Alright, so the left side, we don't need this. You can just delete. What I'm doing is just typing in forward slashes so that we can have comments. The right side is also zero gradient. Actually, no, left side, we need to specify an inlet. Okay. So let's rename it inlet. And that will be zero gradient. Front and back is empty. Right side we don't need to specify. So that is the right one to comment. 2, 3, 4, 5. That should comment everything out nicely. So everything checks out, hopefully. So let's go and check our control dict. This will help us determine time step and everything, so that should be okay. All looks okay now. Okay, we're gonna have our run script. So we clean the case, then we're gonna run OpenFoam for a while. And it's very quickly done. So I'm gonna go to the desktop and I'm going to get our file out. OpenFoam files, extended flat plate, and I'm gonna copy this whole thing over. Okay, maybe for the sake of clarity, I want to remove, or maybe I'll change the run code. I want it to touch flat plate extended .foam. Yeah, because it takes very short, I'll just go do it this way. Very lazy. Okay. Wow, I've got so many files open. I'm gonna close everything. Okay. I have this open. Go to my OpenFoam files. Flat plate extended. I'm gonna copy and paste it here. Okay. So we're gonna open ParaView. Okay, I'm gonna delete these files. This is my archive folder. Yeah. Let's apply. And we look. It's beautiful. Looks beautiful. Oh, okay. So now we see what's this like. This is the pressure profile. You can see a very high buildup of pressure here, and there's some negative pressure over here as well. Okay, let's take a look at the U velocity profile. Okay, so we still have this kind of a strange red zone over here. But if you want to compare it to the old one, it will be as such. Where's my flat plate? Okay, we'll have to port it over as well. Flat plate or flat plate fine, since we already have that. We'll copy over the flat plate fine file. Okay, and we'll look at the ParaView. Okay, flat plate fine. Where's flat plate fine? No, it's not in this. OpenFoam files window. There you go. Flat plate fine.foam. Pressure, velocity. Okay, yeah, it looks a bit weird. But anyway, you look at this. And then you look at this. Okay, you see the profile is also kind of weird. We have this large section where you have this red zone, which, well, basically means it doesn't solve the problem. Okay, there is one more thing we want to alter, of course. That is the grading of the mesh. Okay. Okay, so I'm going to copy this over. Grade it. So I'm going to go to the flat plate graded. Okay, so I'm gonna clean this up as usual. Okay, but anyway, I think the best way is to just stop the video for now. Just let you know that we have successfully altered our geometry. At least that's the successful thing. We have this this front plate front part where the velocity is able to do its thing, become like a free stream. But you still see that you have this pressure buildup in here, and the velocity here is faster than 1. Even if you look at the x magnitude, it's still not quite right, and we are probably wondering why. So the other thing we want to note is to try and troubleshoot the grading here. That means if you look at the previous if you look at the previous ways other people have done this kind of a file, you notice that the mesh size at the bottom is very much smaller than the mesh size at the top, and at this interface between the free stream plate, which is over here, the left hand side and right hand side, at this interface the mesh size is a lot smaller. So how do we do this grading thing? So we're gonna pause the video, stop the video now, and we're gonna visit it in the next video, and we'll see whether that solves our problem. Thanks very much for watching. I'll see you guys next time.